This is video 3 for lesson 2 in unit 8, strong acids and bases for chemistry 2. So we covered Arrhenius acid-base theory, and now we're going to look at one that is a little bit more broad and encompasses Arrhenius theory, but also has some things that wouldn't typically be called an Arrhenius acid or base, counting as an acid or base. So this was developed by Bronsted and Lowry, hence the BL theory, the Bronsted-Lowry theory, and they define an acid as a proton donor. And the proton is H+. So it's something that donates a hydrogen ion or a proton to something else. Well, the something else that it donates it to is a base. A base is a proton acceptor. So in this, an acid-base reaction is defined as a transfer of a proton, an H+, from an acid to a base. So if we look at a reaction, HCl plus HOH. HOH is another way of writing water. We have to think, okay, HCl is a strong acid. Well, we need to know the relative strengths of acids and bases to one another. So you have a reference packet that looks like this. And this is going to help us determine what is going to act as the acid and what is going to act as a base. So if you see one of these things listed, these are all very strong, so these would be acids. But if you were given two substances that are both in this weak area and you don't know which one is the acid and which one is the base, the higher on the list, the stronger the acidic character it has. So if we look, HCl is higher on our list than H2O. So this one is going to be our acid, and this one is going to be our base. So an acid donates a proton to the base. So an H is going to go from HCl and add on to here to become H3O+, and then we're going to end up with Cl-. So we have a transfer of a proton and an acceptance of a proton to the base. Now, these two substances over here have names. This is the conjugate base, and that's the conjugate acid. Notice that we have an equilibrium situation. So the conjugate base is the species remaining after an acid. Have these backwards. Conjugate acid, conjugate base. Species remaining after an acid gives its proton away. So Cl- is our conjugate base. It acts like a base in the reverse reaction. So if we look at the reverse reaction, H3O plus donates an H to Cl to become HCl. And if you notice, the acid and the conjugate base are related to one another because we decrease the H's by 1 and the charge decreases by 1. Now the conjugate acid is the species remaining after the base accepts a proton. It acts like an acid in the reverse reaction. And here, the charge increases by 1. So we can look at an acid or base and determine what its conjugate is going to be. So it says, find the conjugate base for the following. So these have to be acids. So a conjugate base is what remains after it gives a proton away. So we have to remove an H, so NO3, and the charge decreases by 1. This charge was 0, so it becomes -1. H2PO4 would have a conjugate base, so the number of H's decreases by 1, so we end up with HPO4, and the charge decreases by 1, so it is now -2. So in order for something to act like an acid, it has to have an H. If it doesn't, then it can't be an acid. These are bases. Find the conjugate acids. So they must be bases because the base in a conjugate acid is paired. So that means that we increase the number of H's and we increase the charge by 1. So we have to add an H to this. So NH4. It is neutral, so it becomes +1. PO4 becomes HPO4 -2. The charge increases by 1.